going to celebrate National Science Day at our institute. National Science Day is being celebrated every year to celebrate the discovery of Raman effect, which was given by Sir C.V. Raman. It is our pleasure to announce over here that Sir C.V. Raman has graced our institute by his benign presence during the inauguration of our Digwadi building in 22nd April 1950. So today also, celebrate this occasion, we have an eminent scientist of India as our chief guest, Professor A.S.K. Sinha. I would like to request our respected director, sir, and Dr. J.K. Pandey, sir, to accompany our chief guest up to the dais. Thank you, sir. Now, I would like to request our director, sir, to welcome chief guest by presenting flower bouquet and book. Thank you, sirs. Now I would like to request the dignitaries on the dais to inaugurate this function by lightning lamp and garlanding Sri Sir C.V. Raman's photograph. Thank you, sir. Now, moving ahead, I would like to invite our respected director, Professor Arvind Kumar Misra, sir, for his welcome address. Sir, please.
Good afternoon to everyone, and a warm welcome. Honorable Chief Guest of the function, Professor Sinha, who is Director of RGPIT Raebareli, uh, who happens to be alumnus of IIT BHU. We welcome him. On a very short notice, he accepted our invitation to be here on the function of National Science Day. So we are very much thankful to you, sir, because he took in trouble all the way, traveling from Raebareli to Lucknow, and then from Lucknow to Ranchi, and Ranchi to Dhanbad. So it's a long journey for him. And then this morning he had to go to Digwadi campus to interact with the scientists. And I welcome all my fellow colleagues, other staff members, technical, non-technical, respected faculty members from different schools, dear students, research scholars, and those who are connected online, my faculty colleagues, fellow colleagues, and others who are connected online. I welcome you all on the occasion of National Science Day, which is a special day so far as scientific community is concerned, and it is known to all of us that why do we celebrate this. Sir C.V. Raman invented the Raman effect, and based on that, Raman spectrometer came into existence, and that's one of the biggest contribution for which the first Asian, first Indian to get in the Nobel Prize in the year 1930. And this all started with the curiosity when he was traveling from Europe back to India, that why color of ocean is blue. And somebody replied that it's because sky is blue, and so the color of ocean is blue, and that is the reason why his curiosity was there to understanding why is it blue. And he was basically a physicist and a brilliant scholar, and he was basically working on sound. And the problem which he picked up was of optics or of light, and he further tried to explain it, and that is how this came into existence. So in the year 1986, it was decided that we should be celebrating the National Science Day, so that this day is being remembered, and the contribution of science and technology to the upliftment of the life of common man, of the society, of the country can be remembered. And over last few years, few decades, globally, we have recognized that those countries which are number one so far as economy is concerned, so far as technology is concerned, so far as uh, military power is concerned. So they are the one who invested their resources in research and development in science and technology. They are the one who are number one. And as we all know, we are passing through the Amrit Kal, and we have a dream. Honorable Prime Minister has envisioned that by 2047 we will be the Viksit Bharat, and this year's theme is indigenous technologies for Viksit Bharat. And that is the reason why we have realized that it is science and technology with the help of which we will be able to achieve a Viksit Bharat or developed country. And over the past, few years, the investments which have been made in science and technology is growing. We had seen that National Research Foundation last year has been instituted, and that Anusandhan National Research Foundation will be driving the R&D efforts in the country. Apart from Ministry of Science and Technology, the DST, DBT, DSIR. If you look up the indigenous technologies which have been developed in CSIR, there are many which have contributed in the recent past, like Chandrayaan 3 or even Aditya 1, the tests were conducted at the research facility of NAL Bangalore, CSIR NAL Bangalore. Similarly, the recent Jhanki, which was CSIR Jhanki in 26th January, wherein it was the Purple Revolution, and the other one was E-Tractor. So Purple Revolution for the lavender cultivation in Jammu and Kashmir, that is one intervention or of science and technology, particularly from CSIR lab, wherein the income of farmers has been increased to 2.5 times. And Aroma Mission is another one which is going in big way. Then the pharmaceutical, there are a number of interventions of science and technology in all the fields. If you look up here in CSIR-CIMFR, we have developed the gasifier, and we are in the process of getting the hydrogen and methanol from coal. That is one. Then the carbonization is another group which is working on converting the semi-cooking and non-cooking to cooking with the intervention of science and technology. These are the few interventions. But globally, we have realized, nationally also, we have realized that if we have to grow, if we have to become stronger economically, we need to be stronger in science and technology. And it is science and technology only with the help of which we'll be in a position to achieve the Viksit Bharat, which we are dreaming of. And the economy, which is the pace with which the economy is growing. It is only because science and technology is trying to reduce the gap or to act as a bridge between the industries, between the entrepreneurs, between the startups, and the technologies. So it has, like if you look up the bio startups, it has its contribution now present contribution is around 4% of the GDP. So the growth which has come up, DBT has played a very strong role in bringing in that. Similarly, there are other technologies which have come up, let it be DRI or other technologies so far as the steel industry is concerned. Similarly, for making for the target of steel 300 million tons by 2030, another target for which CSIR-CIMFR is also working closely with the ministry so that those targets can be achieved. So this day is being celebrated to celebrate the importance of science and technology. So far as development is concerned, so far as upliftment and better life is concerned of the common people, farmers, downtrodden, society, but downtrodden, section, and the society. So it is society and the country for which the science and technology is the only tool with which we will be in a position to move up and contribute. And as I can see, the bright students from school, they have a big responsibility because they are the one who will be responsible for taking up the country as Viksit Bharat. So, with these words, I once again welcome the Honorable Chief Guest, as well as all scientists, faculty members, teachers, scholars, and students. And I wish this program a grand success. Thank you very much. Jai Hind.
Thank you so much, sir, for your inspiring words. Uh, Before moving ahead, I would like to request the students sitting in this corner to kindly shift those sides so that this screen would be visible to them. आप लोग उधर शिफ्ट कर सकते हैं, ये स्क्रीन ज्यादा विजिबल होगा. Now, I would like to request Dr. J.K. Pandey sir to kindly come and introduce our chief guest, Professor A.S.K. Sinha. Sir, please.
Thank you very much, Himanshu. Uh, Honorable Chief Guest of the today's function, Professor Sinha, respected Director, Sri Alok Sinha Sharma and my fellow colleagues, students, teachers, and all those colleagues who have joined from the online also. It is my privilege and honor for me to introduce the today's chief guest, Professor Sinha, who is our chief guest for today's National Science Day celebration function. Professor Sinha is a product of IIT BHU. He completed his BTech in 1979 from IIT BHU Department of Chemical Engineering, then MTech from the same institute, IIT BHU in 1981, and finally PhD also from IIT BHU itself. And then he started his career, pursued his career as a faculty in the same department. Right from 84, he continued till 2019 when he superannuated. And since then, he is working as a director of Rajiv Gandhi Institute of Petroleum Engineering, Rajiv Gandhi Institute of Petroleum Technology, Raebareli, JAS Raebareli. He has a lot of accomplishments during his career. He a number of publications, maybe more than 180, 15 book chapters, 5 patents, all academic accomplishments are there with him. And as far as clothes are concerned, he is distinguished alumnus awards of IIT BHU, then lifetime achievement award of Indian Institute of Chemical Engineers. His research area where he has contributed very significantly, and he is known for his work on setting up of H2 laboratory, hydrogen laboratory, catalysis laboratory, and sophisticated instrumentation facility at IIT BHU. These are his major and achievement contributions. And as a director of the IIT, this RGIPT, besides many other things, his compassion for the local to global can be visualized through various social outreach schemes such as Gyan, Arpan, Rise, Sauhard, initiated by him under the umbrella Project Amethi. These are a special initiative by Professor Sinha under the local to global scheme of the Government of India. With this, although even a brief data is very long, with this his brief sketch, we are very happy to welcome him here in this today's function of National Science Day, and we are honored to have him as a speaker for the National Science Day function of today's at CSIR-Central. With this, we request him to this. Thank you very much.
आप सभी को नमस्कार। प्रोफेसर प्रोफेसर मिश्रा जी, डायरेक्टर, डॉक्टर पांडे जी। डॉक्टर पांडे जी is we passed out from the same institute. He is junior to me. When Mr. Sharma, distinguished scientist of CIMFR, technical persons, school students, I feel very happy when the school students are sitting, because they are the future of the country and they have a lot to do for the country also. And their teachers. I feel very happy that I am here before you and interacting with you. In fact, it is an honor to me that I am given the opportunity to address this distinguished gathering of scientists and technical people of CIMFR and the students. For that, I thank the director. Though it was a long journey, but the pain of the journey does not count when I have the opportunity to interact with you. So thanks to the director that he has given me the opportunity. Now, whenever I go, I take some time to introduce our institute. It is a new institute, so being the director, I take the responsibility to let others also know what is the institute. And I will use a mixed language. Sometime I will also speak in Hindi, because I feel that हिंदी बोलने से बात ज़्यादा समझ में आती है, तो मैं कभी कभी हिंदी भी बोलूँगा। और मेरे साथ डायलेमा ये है डायरेक्टर साहब कि मैं अमेठी जिला के हिंदी प्रचार प्रसार कमेटी का अध्यक्ष हूँ, तो मेरे लिए वो भी एक मुद्दा हो जाता है कि जहाँ संभव हो वहाँ हिंदी में ही बात किया जाए. So I will prefer using both English and Hindi. The Rajiv Gandhi Institute of Petroleum Technology has been established by Government of India by an Act of Parliament, और it has been given a status of institution of national importance. राष्ट्रीय महत्व का संस्थान जैसे IIT होते हैं, और भी कुछ करीब 104 इंस्टीट्यूट हैं इंडिया में जिसको ये स्टेटस प्राप्त है, जिसमें एक वो भी है. The act was passed in 2007-8, but our building came up in 2016. It is in the district Amethi. Amethi तो सब लोग जानते ही हैं. It is a very popular, not popular, famous place. So we belong to Amethi district, and it is an academic institution, and our task is to teaching as well as research. So we have number of BTech programs, BTech petroleum engineering, chemical engineering, and then few other branches are also there. हम लोग JEE एडवांस से एडमिशन लेते हैं, जैसे कि IITs में होता है. कुछ सीट यदि लेस पॉपुलर है तो JEE मेन से भी भर लेते हैं, बट मोस्टली इट इज बाय JEE एडवांस. और भारत सरकार NIRF रैंकिंग देती है इंस्टीट्यूशंस को, मिनिस्ट्री ऑफ एजुकेशन. तो हमारा रैंक नया इंस्टीट्यूशन है, तो 2019 बिफोर 2019 वी वर नॉट एबल टू गेट एनी NIRF रैंकिंग, but 2 years back we got 183 rank. Last year it was 79 rank, and this is the single institution which got a jump of 104 rank in a year. This year we are hoping to be around between 50 and 60. So institute is progressing well, and though we do not want a competition, but for the sake of information, I will say that 4 IITs and 16 NITs have lower rank than what RGIPT has, and all triple ITs except two are lower ranked. So institute is progressing well. It is all the effort of faculty members and students. They are hardworking. So our ordinance, etc., are same as of IIT. The only difference is that we are governed through Ministry of Petroleum and Natural Gas, whereas IITs are governed by Ministry of Education. And also, the we focus in the area of energy. हम एनर्जी के क्षेत्र में काम करते हैं. So there is a synergy between CIMFR and RGIPT because both work in the area of energy. हम थोड़ा सा हाइड्रोकार्बन और पर ज़्यादा फोकस करते हैं और यहाँ पे कोल पे फोकस है. बट नाउ CIMFR is also shifting towards new energy, newer energy, sustainable energy, and we are also shifting to newer energy. So there is a lot of synergy between the two institutes. And as Professor Misra said, in the morning I went to the fuel research, earlier erstwhile Fuel Research Institute. I interacted with the scientists there. It was a very good interaction, and there are a number of areas where we can collaborate. And I will trouble Dr. Pandey and Dr. Banerjee Saab, that we'll have video conferencing soon, and we'll find out what are the areas where we can work together for the benefit of both and ultimately for the country. So this is and we have two centers also. Act has given us authority to open centers at different locations. So we have one center in Assam, Shivsagar. There we run diploma programs, and one is in Bangalore, where we focus on transnational research and digitalization and AIML types of activities are there. So with these words, I come to my talk. I have selected sustainable energy transition in India. First, we pay homage to Sir C.V. Ramanji, our all respect. Then I will start with one quotation because our students are there. So what is it is from Paul Hawken, the author of Blessed Unrest. What is the situation now? At present, the statement is very, 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 we must understand. At present, we are stealing the future. Futures, selling it in the present and calling it gross domestic product. We can just as easily have an economy that is based on some spelling mistake, based leading the future instead of stealing it. We can either create assets for the future or take the assets of the future. इसका कहने का मतलब है सीधा सीधा कि अभी जो हम कर रहे हैं, दो ऑप्शन हमारे पास है, या तो फ्यूचर के एसेट को प्रेजेंट में यूज करें या हम फ्यूचर के लिए एसेट करें, एसेट क्रिएट करें ताकि जो फ्यूचर जनरेशन है उसको यूज कर सके. अभी हम उल्टा कर रहे हैं, जो फ्यूचर का होना चाहिए उसको अभी करंट में हम, तो वन इज कॉल्ड एक्सप्लॉयटेशन, अदर इज कॉल्ड रिस्टोरेशन. सो अभी हमारे जितने जाने अनजाने में जो भी हमने काम किया, दैट वाज एक्सप्लॉयटेशन ओनली. ये इस तरह का सिचुएशन है जैसे कि हमारा खर्चा नहीं चल रहा हो तो हम अपना जो एसेट है उसको गिरवी रख रहे हैं कि फ्यूचर में जो आएगा वो उसको छुड़ाएगा. तो दैट इज व्हाट वी आर डूइंग नाउ. सो दिस इज we have to understand and we have to correct ourselves. So there is now great concern and we are now thinking of how to restore the earth. And there are three major problems. One is the erosion of topsoil. And because of that, there is likely to be food scarcity. दूसरा, पानी, water table is going down. There is likely to be water scarcity. तीसरा, हम लोग ने excessive फॉसिल फ्यूल इस्तेमाल किया. फॉसिल फ्यूल वो है जो जमीन से निकालते हैं. तो इसकी वजह से क्लाइमेट चेंज एंड ग्लोबल वार्मिंग का प्रॉब्लम फेस कर रहे हैं। तो ये 3 मेजर प्रॉब्लम है। हालांकि यूनाइटेड नेशंस ने 17 सस्टेनेबल डेवलपमेंट गोल डिफाइन किया है एंड कुछ टारगेट रखा है 2030 के लिए, ताकि जो हम लोगों ने गलती किया पास्ट में उसको सही किया जा सके। मैं नीचे वाले पे फोकस करूंगा बिकॉज वी आल्सो डील इन द एरिया ऑफ एनर्जी क्लाइमेट चेंज। इन the conference which is held annually is called, abbreviation is COP. So COP 21 सेमिनार हुआ था जहाँ की वर्ल्ड लीडर्स इकट्ठे हुए, यूएन क्लाइमेट चेंज कॉन्फ्रेंस। ये पेरिस में हुआ था दिसंबर 12 2015 को। वहाँ ये डिसाइड किया गया हाउ टू टैकल द क्लाइमेट चेंज एंड इट्स नेगेटिव इम्पैक्ट्स। और वहाँ कुछ डिसीजन हुए कि हम लोगों को इस तरह का कार्य करना है ताकि जो अर्थ का टेम्परेचर है 1.5 डिग्री से ज़्यादा ना बढ़े प्री इंडस्ट्रियल टाइम से। व्हाट इज द रीजन ऑफ दिस इंक्रीज इन टेम्परेचर? मैं किसी स्टूडेंट से पूछूं तो पता चलेगा? व्हाई दिस ग्लोबल वार्मिंग? बैठ जाइए। कार्बन डाइऑक्साइड विच वी एमिट, कार्बन डाइऑक्साइड का हमारा बहुत दिनों से 200 ppm पे कार्बन डाइऑक्साइड का कंसंट्रेशन होता था, अब वो बढ़ के 400 हो गया है, जिसके कारण से फॉर दैट वी आर नॉट the infrared which comes in the daytime due to from the sun, it has high frequency, it can reach to the earth. लेकिन जब रात को धरती से जो हमारा इंफ्रारेड निकलता है जिसको वापस चले जाना चाहिए, उसकी फ्रीक्वेंसी लो होती है, लॉन्गर वेवलेंथ होता है, उसको कार्बन डाइऑक्साइड जाने नहीं देता। कार्बन डाइऑक्साइड की तरह और भी गैस है जिसको हम लोग ग्रीन हाउस एमिशन गैस बोलते हैं। तो ये चूंकि कार्बन, देयर आर नंबर ऑफ गैसेस विच आर मोर पोटेंट, जिसकी क्षमता ज़्यादा है, लेकिन चूंकि उसकी मात्रा कम है, इसलिए CO2 को हम लोग मेजर कल्प्रिट बोलते हैं। यदि हम नहीं इसको कंट्रोल करेंगे तो कुछ दिन में ये 600 ppm हो जाएगा और तब हमारा अर्थ का टेम्परेचर अराउंड 2 डिग्री राइज करेगा। अभी की स्थिति ये है कि हमने 1.5 पे कंट्रोल करने का सोचा, लेकिन अभी हम 1.1 तक पहुंच गए हैं। और जिस रेट से यदि कार्बन डाइऑक्साइड यदि हम इमिट करें तो ये 1.5 जो है 2035 तक पहुंच जाएगा। वी विल रीच cross the 1.5 degree by 2035. So time is very less and we have to act. So accordingly, every 133 countries are signatory to this Paris Agreement, and they have to, every 5 years, they have to give their nationally determined contribution, or we call NDC, कि हम आगे 5 साल क्या करने जाना है, and it is binding. So India also, it is called COP26 meeting, which was held in Glasgow. India also gave what the target for India, the country is, and Prime Minister called it Panchamrit. And I have listed it, it is visible. So in this, we say that our renewable energy, mostly solar energy contribution, will be 50% of the total energy requirement. And the last is that we want to achieve net zero emission by 2070. Net zero means जितना हम कार्बन डाइऑक्साइड emit करेंगे उतना कार्बन डाइऑक्साइड वापस ले लेंगे. That is called net zero emission. So 2070 तक हमें net zero emission टारगेट अचीव करना है. दिस इज आवर इंटरनेशनल कमिटमेंट, और इसको फुलफिल करना हम सारे साइंटिस्ट और सारे लोगों का कर्तव्य है. So what is the, I will come to what is the present energy scenario. We know that Indian economy will expand to $5 trillion by 2025 and $10 trillion by 2030 from current $3 trillion. So we have to develop also, Viksit Bharat. And if डेवलपमेंट के लिए एनर्जी की आवश्यकता भी होती है, its share in global energy demand is expected to double from the current 6% to 12% by 2050. 2050 तक वर्ल्ड का 12% एनर्जी जो है इंडिया कंज्यूम करेगा, अभी 6% है, तो कितना कितना ज्यादा इंक्रीज होने वाला ये दिखाता है. It is already the fourth largest energy consumer, with primary energy consumption doubling in the last 2 decades, and is poised to become the third largest consumer by 2030. And over 80% of energy needs of the country is met by 3 fuels, that is coal, oil and solid biomass. हमारी जितनी रिक्वायरमेंट है उसका 80% कोल, ऑयल एंड बायोमास से आता है. कोल से 44% आता है, 44% फ्रॉम कोल. Oil makes around 25%, 6% from natural gas, and the rest is from biomass and a small contribution from renewable energy. Carbon dioxide emission, though it is very low on the per capita basis, but because the country is large, 140 crore population is there, so if country-wise we go, we are the third largest emitter of CO2 after USA and China. So there is a lot of pressure, international pressure on India to reduce carbon dioxide emission. Now, one figure I have got from somewhere, it says that India's energy sector related CO2 emission have more than quadrupled since 1990, with the major source of emission growth being power generation, जो thermal power plant है. Industry and transport. Coal is responsible for 70% of India's energy sector CO2 emission. 70% emission coal को जलाने से होता है. The carbon intensity of India power sector is, this figure again you should look at. 1 किलोवाट आवर एनर्जी जनरेट करने के लिए इंडिया में 725 ग्राम कार्बन डाइऑक्साइड एटमॉस्फेयर में जाता है, जबकि ग्लोबल स्टैंडर्ड 510 है. तो हम बहुत ज्यादा कार्बन डाइऑक्साइड emit कर रहे हैं because our thermal power plants are inefficient. Then energy transition throughout the world is going to a transition to clean low carbon source of energy at an unprecedented pace and scale. हम लोग चाहते हैं कि अब जो लो कार्बन सोर्स एनर्जी को यूज किया जाए. New technologies are required to replace existing fossil fuels. Now it is because market of India is very large, so it is a strategic importance for India, which will be one of the world's largest market for these technologies in the decades to come. India needs to position itself at the technology frontier to maximize the benefit of the energy transition. We should be technology maker, not the technology taker. Now, if we see the current scenario, there are few clean energy technologies which have dominated the energy transition so far, namely solar photovoltaic, wind, and lithium-ion batteries. We all know that these are the new source of energy. But there are certain limitations to electrification. There is a cost barrier. Then there are other regions also. So complete electrification is not possible. In the transport sector, if we compare the heavy duty vehicle, there is yes. For example, in the transport sector, you have seen that small 3-wheeler have now battery operated. Cars are also battery operated. But a calculation says a liter of gasoline, 1 लीटर गैसोलीन का वजन करीब 0.75 kg होता है, जिसमें 35 मेगाजूल एनर्जी होता है. सिमिलर एनर्जी के लिए लिथियम बैटरी यदि यूज करेंगे तो उसका वजन 50 kg होगा. तो अब बड़े ट्रक बस में जहाँ की 100 लीटर डीजल भरा के चलते हैं या उससे ज्यादा, तो बैटरी का वजन कितना होगा ये आप गेस कर सकते हैं. इसलिए भारी व्हीकल में बैटरी संभव नहीं है. बैटरी थोड़ा सा वो उसका इंजन एफिशिएंट होता है, उसके बाद भी हेवी व्हीकल के लिए अब संभव नहीं है. उसी तरह एविएशन सेक्टर में भी बैटरी संभव नहीं है. सो व्हाट इज द देन ऑप्शन? उसी तरह इंडस्ट्री में जहाँ हीट करने की जरूरत है, हीटिंग की जरूरत है, वहाँ बिजली से हीट करना मुश्किल है. तो कंप्लीट इलेक्ट्रिफिकेशन पॉसिबल नहीं है. देन बैटरीज में एक प्रॉब्लम और है, लॉन्ग टर्म चार्जिंग डिस्चार्जिंग की वजह से ये भी संभव नहीं होता है. then there are challenges. Then what could be the future source of energy? So then what is the likely future strategy for India? India को क्या करना चाहिए? So India is already the fourth largest energy consumer, with primary energy consumption doubling in the last 2 decades. And there has been a number of policy changes, and policy has focused on the accelerated and ambitious plan to increase the contribution of alternative source of energy such as renewable, green hydrogen, biogas, ethanol blending, and CCUS, carbon capture, utilization, and storage. I will come to that later. So India's future prosperity will hinge on affordable, clean, and reliable energy, and the scope for further growth in energy demand and infrastructure is huge. Solar power is set to for explosive growth in India, matching coal's share in the India's power generation mix within 2 decades. Today, clean energy momentum enables India to outperform. हम लोगों ने जो पेरिस एग्रीमेंट पे प्लेज किया है उससे बेहतर हमने अभी परफॉर्म किया है. India must also ensure that energy transition does not result into foreclosing its development option. हमें डेवलप भी करना, विकसित भी होना है, तो इसलिए हमारा जो डेवलपमेंट प्लान है वो भी स्मूथ चलना चाहिए. कम्युनिटी को भी इसके बारे में जागरूक करने की जरूरत है कि हमें कार्बन डाइऑक्साइड एमिशन कम करना है. Coal will remain in the short to medium term. Processes such as supercritical technology with higher efficiency, as I said that our power plants are inefficient, so retrofitting is possible so that carbon emission reduces. And if we are practical, then we have to say that coal has to remain. Then if coal has to remain, then we have to develop carbon capture, utilization, and storage technology as well. And the gas will be a bridging fuel. Gas means natural gas because it is CH4, so emission is less compared to LPG or liquid gasoline. Accordingly, in recently held COP28, which was held in Dubai, I think 3 months back, the Prime Minister of India reiterated the country's renewable energy commitments. Prime Minister ने कहा कि जो हमारा renewable energy का commitment है वो हम उस पे तेजी से आगे बढ़ रहे हैं. But at the same time, government has been unequivocal about coal's importance in the country's economy. ये भी कहा गया कि कंट्री के इकोनॉमी में कोल का बहुत इंपॉर्टेंट है, इसलिए हम कोल को खत्म नहीं कर सकते. Then there are hydropower. Hydropower can play a role. Building up and import of hydropower from Nepal and Bhutan is a long-term solution. Power sector accounts for only 45% of India's emission. So rest 55% emission comes from industry and transport. So केवल पावर सेक्टर के एमिशन को कम करने से काम नहीं चलेगा, और भी जगह जो ट्रांसपोर्ट, रेजिडेंशियल, इंडस्ट्री, सबको देखना पड़ेगा. So electricity will be the dominant part of the overall energy system, and most of the energy will be used for hydrogen production, which will be ultimately used in industry and transport. अभी हम हाइड्रोजन इलेक्ट्रिसिटी से बनाते हैं, बट हमको हाइड्रोजन जो है सोलर थर्मल से भी बनाना पड़ेगा. हाइड्रोजन का डिसोसिएशन यदि हम करें तो 1100 या एग्जैक्टली आई डू नॉट रिमेम्बर, बट सम 1000 डिग्री टेम्परेचर चाहिए. सो हम सोलर थर्मल को भी यूज करके हाइड्रोजन बना सकते हैं, वाटर को डिसोसिएट कर सकते हैं, वो भी करना पड़ेगा. लैंड का रिक्वायरमेंट भी देखना पड़ेगा. यदि हर जगह हमने सोलर फोटोवोल्टाइक लगा दिया, देयर विल बी ह्यूज रिक्वायरमेंट ऑफ लैंड. Then the fundamental benefit of biofuel is that they may provide a low carbon alternative to fossil fuel. Actually, biofuel is a carbon neutral thing. The carbon dioxide is absorbed by the plants, so we get biofuel, and carbon dioxide is again emitted, which is again taken by the plants. So biofuel is a low carbon alternative to fossil fuel based liquid transport fuel such as gasoline, diesel and aviation fuel. फ्यूचर में ये जो गैसोलीन, डीजल एंड एविएशन फ्यूल है, ये हमको बायो रूट से बनाना पड़ेगा. एंड यदि आप लोग को याद होगा तो अभी G20 नेशन का जो समिट हुआ था, उसमें एक इंडिया, ब्राजील एंड US अलॉन्ग विथ 12 इंटरनेशनल ऑर्गेनाइजेशंस ने मिलके एक ग्लोबल बायोफ्यूल अलायंस बनाया है फॉर टेक्नोलॉजी इन्वेस्टमेंट, expert collaboration and global standards to reduce hydrocarbon reliance. So there are a number of things being done at the government level, at the industry level. दूसरा एक ऑप्शन ये हो सकता है, एज ए डेंस सोर्स ऑफ एनर्जी न्यूक्लियर पावर कैन प्ले अ रोल. सो न्यूक्लियर पावर से हम हीट पैदा करें और उस हीट को यूज करके वाटर डिसोसिएट करें और हाइड्रोजन जनरेट करें, एक ये भी हो सकता. तो इन सब के लिए बहुत ज़्यादा R&D की ज़रूरत है, और हमारे यंग लोग जो बैठे हैं, दे हैव टू टेक अप द चैलेंज फॉर द फ्यूचर. सिम्फर में है, हमारे यहाँ भी हैं, सब जगह है. सबको ये करना पड़ेगा ताकि जो हमारा ग्लोबल, हमारे सर्वाइवल के लिए ज़रूरी है. यदि इस तरह से चलते रहे तो हम 2035 में तो 1.5 डिग्री का जो वो है पार कर जाएंगे, और अगले 20 साल में हम 2 डिग्री राइज देखेंगे, तो बहुत ही मुसीबत में पड़ेंगे. तो हम सबका मतलब इट इज़ अ वेरी सेंसिटिव मैटर एंड एवरीवन हैज़ टू कलेक्टिवली वर्क. Then, as I said, that we cannot do away with carbon, so coal. So we have to develop technology which capture carbon, utilizes carbon, and store carbon. So इस दिशा में भी काम हो रहा है. There is a term called sustainable aviation fuel, because for aviation के लिए तो हाइड्रोकार्बन ही चाहिए. तो उसको यदि हम कार्बन डाइऑक्साइड कैप्चर करके फिर उसको एविएशन फ्यूल में कन्वर्ट करते हैं, देन इट इज़ कॉल्ड SAF, सस्टेनेबल एविएशन फ्यूल. एंड गवर्नमेंट का मैंडेट है कि 1% आपको जो ATF होता है, एविएशन टर्बाइन फ्यूल, उसमें 1% अभी सस्टेनेबल SAF मिलाना है, कंपलसरी है. उसी तरह 20% एथनॉल मिलाना पेट्रोल में कंपलसरी हो गया है. So there are number of things being done, and we are quite hopeful that we will achieve the target. So carbon capture के बहुत सारे टेक्निक है. I will not go into the detail, but all are very capital intensive. बहुत ज़्यादा पैसा लगता है, तो R&D breakthrough is required. Similarly, carbon is a useful material also. अभी कार्बन डाइऑक्साइड कहाँ यूज करते हैं? Some of the uses of carbon dioxide as of now, अभी कहाँ यूज करते हैं? कोई बताओ. Biggest user is fertilizer industry. Ammonia plus carbon dioxide gives urea. Carbon dioxide. Then there are other application also. ऑयल एंड गैस इन्हांस्ड रिकवरी के लिए EOR बोलते हैं, इन्हांस्ड ऑयल रिकवरी. CO2 जब इंजेक्ट करते हैं पुराने वेल में, तो वहाँ से ऑयल रिकवरी थोड़ा सा फास्ट होता है. देन इट इज यूज्ड इन द बेवरेज, सब लोग पीते हैं एरेटेड बेवरेज. देन यू राइटली सेड फॉर द फूड प्लांटेशन. देन इट इज यूज्ड फॉर कूलिंग, metal fabrication, etc. So these are the current uses, but we will have to find out the new uses of CO2. For example, in the production of building material, in the conversion to fuel, conversion to polymer, plastic. So these are the new areas which are of the current area of interest being pursued in the research laboratories. But one thing we must understand that carbon used is not same as carbon dioxide avoided. So in the ultimate run, we will have to avoid carbon dioxide. कार्बन डाइऑक्साइड यूज करके हम कितना कार्बन डाइऑक्साइड वापस ले लेंगे, ये तो संभव नहीं है. तो कार्बन डाइऑक्साइड के यूज को कम करना ही पड़ेगा. और सेकेंड थिंग है कि इफ यू कैनॉट यूज कार्बन डाइऑक्साइड टू कलेक्ट कार्बन डाइऑक्साइड एंड देन स्टोर इट इन द अंडरग्राउंड माइंस एटसेट्रा. कार्बन डाइऑक्साइड स्टोरेज एंड सिक्वेस्टरेशन. सिक्वेस्टरेशन इज समथिंग इन नेचर में भी कार्बन डाइऑक्साइड साइकिल होता है. You remember that carbon dioxide which is emitted is taken by the plants and then and converted into cellulose, and when the cellulose is burnt it gives carbon dioxide. So there is a cycle. Nature itself regulates the carbon dioxide, and that is known as sequestration. But now it has become beyond the nature to regulate the carbon dioxide, and this concentration is rising, and then artificially storage, that the word is storage. So these are the techniques we will have to adopt. We will have to do research so that it becomes cost effective, because at present we cannot do away with fossil fuels. So there is a term called hydrogen economy. A concept called hydrogen economy based on hydrogen energy system was put forward in 1970s, in which hydrogen was proposed as a major energy vector. There are many advantages of using hydrogen as energy source. It includes hydrogen production, storage, transport, and utilization, all. So water is used. Water is H2O. It can be broken into hydrogen and oxygen. And when hydrogen is burnt again, so hydrogen and oxygen combines, it brings back water. So it is completely reversible cycle. And if this energy comes from solar, non-carbon sources, then this hydrogen is called green hydrogen. So, and the advantage is that you know that if $1 of crude increase in price of crude by $1, all from the share market to vegetable market, all are affected, because it is concentrated in some part of the world, Middle East or Russia or USA. So the country is very vulnerable in that sense, because we are 85% of our crude is imported, and 50% of gas is imported. So we are very vulnerable. But if we are successful in getting energy, converting solar energy into hydrogen by dissociation of water, then water is distributed everywhere. We also have plenty of water and sun. So our dependence on import goes down, and CO2 emission also goes down. There are a number of advantages. So therefore, we are promoting hydrogen as a source of energy. So this is some picture which says on the left side there are a number of ways which hydrogen can be produced, and then it is used for heating, for mobile application, etc. This is also the same thing. There is a fuel cell. Fuel cell is where you allow hydrogen and oxygen to react electrochemically so that electricity is generated, and that electricity can be used for is a source of energy. So I said that it has a number of advantages, but there are challenges also we have to address. That it is not free. It is always found in combination with other element like water. It is combined with hydrogen, oxygen. Its buoyancy, flammability. There are many things. Those are we have to address. Storage is a big problem because it is a light gas. The current status is that at present we produce hydrogen by methane reforming. Again, it is called gray hydrogen, because we are using carbonaceous source, methane. So it is called gray hydrogen. And when we steam reforming gives you hydrogen and carbon dioxide, if you somehow capture carbon dioxide, then it is called blue hydrogen. So, but our aim is to have green hydrogen. So most promising route is splitting of water. Then there are a number of other techniques also. I think I have less time left. So biological route is one of them. Biomass. Yes, this is the electrolyzer. So there are three different types of electrolyzer. Two are commercial. One is called proton electrolyte membrane, in which you can see that there is a membrane in between the central part. Then there is a cathode, there is an anode, and this membrane is of typical type. It allows only proton to go from one end to another end. So you get hydrogen and oxygen. My pointer is not working. So in case it is acidic, so H plus is the charge carrier. The second one is alkaline. Here we have OH minus is the charge carrier, and alkaline fuels, alkaline electrolyzers are more efficient compared to acidic, but there is some disadvantage as well. The gap between electrode is high, so resistance become high. And the third one is being developed where this proton exchange, we have OH minus exchange. So this is under development. So there are a number, and this shows that this is a modular type of thing. If you want more electricity, we can have number of modules connected together. So this is modular arrangement. These are the components of one typical electrolyzer. Now this is an important figure. On the left hand side, you see the hydrogen cost, and there are two major costs. One is the cost of electrolyzer, and another is the cost of electricity. So if the current at present, we have around $40 megawatt hour. If it comes down to say 20, and the electrolyzer cost also comes down to say $400 per kilowatt, then the hydrogen produced will be commercially viable. At present, it is around $5 per kg, whereas steam reforming gives you between $1 to $2 per kg. So there is a large difference, and a lot of research is going on to bring down the cost of the green hydrogen by reducing the cost of electricity as well as the electrolyzer. One is the operating cost, another is capital cost. And if we are able to bring down to some extent, then it will be a win-win situation for us. This I can escape. Now there is another design. In the first one, you see that there is a large gap between the two electrodes. And because of the difference, there is a ohmic resistance also. So another design says that there is a zero gap electrolyzer is there, second one. So this is one of the advancement to reduce the cost of electricity, energy requirement. If you compare, first one is polymeric electrolyzer, second is another type anionic electrolyzer, then alkaline, and then solid oxide electrolyzer, and the parameters are there. If you see the energy requirement, first column, last but third line, the electricity requirement, it ranges from 47 to 66 kilowatt per kg hour. Now, theoretical requirement is from the thermodynamics, if you calculate, it will be 39 kilowatt hours. So there is a lot of scope of efficiency, improvement in the design, improvement in the electrode, everything. So this is one area of the research. Now coming to briefly discussing what we do, I have selected only 2-3 things. The commercial electrolyzer requires very pure water. That is the impurity level or dissolved solid level should not be more than 5 ppm. So it is very stringent requirement. And India has shortage of potable water also. So a challenge was given to us by NTPC that whether we can develop some electrolyzer which can directly take the seawater. We have plenty of seawater. द डिफिकल्टी फॉर सी वाटर के साथ दिक्कत यह है कि उसमें क्लोराइड आयन होता है जो कि ऑक्सी क्लोराइड में कन्वर्ट हो जाता है और ऑक्सी क्लोराइड फिर इलेक्ट्रोड को कोरोड कर देता है. दैट वाज द प्रॉब्लम. एंड द सेकंड इज दैट मेम्ब्रेन काम नहीं करेगा क्योंकि डिजॉल्व सॉलिड है, वहाँ डिपॉजिट हो जाएगा और इलेक्ट्रोलाइट जो लेफ्ट राइट जाता है, जो इलेक्ट्रोलाइट का मूवमेंट होता है फ्रॉम दिस चैम्बर टू दिस चैम्बर, वो नहीं हो पाएगा. तो वी टुक अप द चैलेंज. वी वर वेरी not sure that will it be possible or not. So we worked and we could develop 3 electrode which were equally active and durable as well. We did some engineering so that chloride ion could not reach to the electrode, and so our electrode was not corroded, and we run it for 2000 hours with the same activity and durability, and these 3 electrodes are patented also. So this was the one work. Then there was need to find out the design of electrolyzer. So because we cannot have membrane in between, otherwise it will clog down. So we designed a flow electrolyzer. So there were 2 chambers. It is very small picture in the at the bottom. It has 2 chambers and water flows. So it allows the hydrogen to go on one side and oxygen to go on one side without mixing. So this was also designed by us and given to NTPC. Now they are scaling it up. And this is the complete system, how to pump, etc. Then one interesting thing which I will like to explain the particularly school student. This is also where we are working. अभी क्या होता है कि ये हमारा 2 इलेक्ट्रोलिसिस है, 2 स्टेप प्रोसेस है. फर्स्ट स्टेप में हम फोटोवोल्टाइक सेल लगाते हैं जिससे हम इलेक्ट्रिसिटी पैदा करते हैं और उस इलेक्ट्रिसिटी को फिर हम इलेक्ट्रोलाइजर में देते हैं जहाँ की हाइड्रोजन. सो एवरीथिंग इज इलेक्ट्रॉन. So can't we combine these 2 processes ताकि ये सिंगल स्टेप में हो, and that will become more efficient. यदि हमारा 12-13% या उससे भी कम इफिशियंसी आता है यदि दोनों सिस्टम को कंबाइन करें, तो एक सिस्टम में उससे ज़्यादा इफिशियंसी आएगा. और ये हम लोगों ने करके देखा. होता ये है, दिस इज द स्पेक्ट्रम ऑफ सन. So sun contains UV range. Blue one is UV, green one is visible, and red one is the infrared. So जो एनर्जी विजिबल लाइट का है वो उसको हम यदि कैलकुलेट करेंगे तो इट विल बी बिटवीन 2 to 2.8 इलेक्ट्रॉन वोल्ट होता है. सो यदि हम एक सेमीकंडक्टर बनाएं, जैसे लेफ्ट साइड में वी डू नॉट हैव पॉइंटर एनीवे. सो यदि आई थिंक दिस वन इज बेटर. ये 2 लाइन हॉरिजॉन्टल जो दिख रहा है, ये 2 एक सेमीकंडक्टर है जिसमें एक कंडक्शन बैंड होता है, एक वैलेंस बैंड होता है. तो जब व्हेन द लाइट फॉल्स ऑन द सेमीकंडक्टर, yes, now when the light falls on the semiconductor, it has sufficient energy. If this band gap is not more than 2.2 or 2.4 electron volt, then electron will come to this conduction band, and a hole is created, positive hole. And this electron, if the redox potential of water is this, then this electron has sufficient energy to come down here and convert H plus to H2. So in a single step, I can convert I can dissociate water, and hole will be electron will come from here to here, and oxygen will be evolved. So it complete cycle works, and this electron is concentrated in a metal, some metal, so that the drawback of this is that once electron has come to this point and hole is there, now the electron can go to either go to react with H plus ion, or it can come back again to the valence band and combine with H plus ion and produce heat. So this is the example, but we have used number of semiconductor, TiO2, sodium, cadmium sulfide, and many things. This is just two example. So the strategy is how to restrict the recombination. This electron should not go to this. All electrons should go to this. Then it will increase the efficiency. So we have done number of work on this. Now, in this you see that oxygen is also produced. So hydrogen and oxygen is an explosive mixture. Can we do something so that oxygen is not produced? It is also possible. Suppose I have this. If you take this one, then the conduction band is there. The electron here can reduce water, but the water cannot be oxidized to hydrogen, so some electrolyte has to be there, which gives electron. So typically, what I did, there is a water and sulfide mixtures are there. So when electron falls, when light falls, the electron reduces is to water, and this sulfide consumes the whole and convert to thiosulfate. So this takes place in one chamber. So we get only hydrogen and sulfide converted to thiosulfate. Now this thiosulfate goes to another chamber where there is some suitable electrode is there, which cannot reduce because the conduction band is not so placed so that it can reduce water, but it can oxidize water to oxygen. And this sulfide takes up the electron. Instead of water taking the electron, sulfide can take electron and converts to sulfide. Thiosulfate takes the electron and converts to sulfide and sulfide. So what is happening if you add these two, the net reaction is H2O giving hydrogen and oxygen. So one chamber hydrogen is produced, another chamber oxygen is produced, and this electrolyte, which is combination of sulfide and thiosulfate, recirculates. In one chamber it oxidizes, another chamber it reduces. So it becomes a continuous process. And there is no need of electrolyzer, there is no need of photovoltaic cell. Light directly falls on the semiconductor material and we carry out this reaction. So this is possible, and we have done, and we are further doing so that the recombination is reduced, brought to zero, and so it becomes more efficient compared to the two-step process. These are the desire of now the same semiconductor which was particle there, we can make electrode. So this is photoelectrode, this is normal electrode. Light falls on this. Uh, Electron and holes are generated, and these electrons and holes generate hydrogen here. If it is p-n type semiconductor, so then hydrogen will be generated here, oxygen will be here. If it is p-type, then hydrogen will be generated on the photo electrode and oxygen on normal electrode, and it is possible that both the electrodes are photoelectrodes. So different configurations are possible. We are also working on this. Now, I will come better understanding. I will finish in 5 minutes. So I said that the semiconductor has a band gap of 2 electron volt. That means any light which is of the wavelength shorter than this will activate the semiconductor. Longer wavelength becomes useless because they do not have sufficient energy to get the electron transferred from the valence band to the conduction band. So can we have design something which where this infrared part of the light can also be utilized for splitting of water? So there are materials which are known as up conversion materials. Up conversion materials are those materials which takes two photons of lower energy and converts it to higher energy. So that way, the lower energy spectrum, the solar spectrum, which has lower energy light also, can be converted to high energy by using the up converting material. And then that up converting material will uh, uh, dissociate water. So that way we are using the infrared part also. That also we have done, and we have found that our efficiency becomes much high. This is what we have shown here. Efficiency becomes much high. So these are the areas of research. Then one more thing which I want to address, that biomass, production of hydrogen from biomass is that you gasify it and then get carbon dioxide and hydrogen, gasification and reforming. So that way you are emitting carbon dioxide to the atmosphere, though we call it biogenic and neutral. So another technique which we are developing is that now this cellulosic, lignocellulosic biomass can be conveniently converted to ethanol by fermentation. It is more established and it is eco-friendly also compared to gasification. And then this ethanol plus water uh, can be electrochemically reacted, and we get 2 moles of hydrogen and 1 mole of acetic acid. No carbon dioxide is there, and acetic acid is equally valuable as ethanol. So 1 mole of ethanol, 1 mole of water gives 2 mole of hydrogen. One comes from water and one comes from ethanol. We get 2 mole of hydrogen and no carbon dioxide. So it becomes carbon negative technique. We are taking out carbon from the atmosphere. So like that, we have to do R&D. We have to think out of box, and the solution is possible. And so that we can save our earth, we can fulfill our international commitment. Government is very keen, doing all support. We have to come forward and provide the solution for younger future generation. Thank you very much. Thank you for giving me the time.
Uh, sir is asking that if anybody is having any question. Uh, Anybody from audience is having any question? Okay, thank you so much, sir, for your insightful Science Day lecture. We have been definitely benefited with the whatever you have presented. It has given us insight about not only what is the problem, but what is the solution as well, uh, especially for energy transition in India. Moving ahead, we have in the morning we had conducted one quiz competition for the school children. So we have to felicitate the winners of the quiz competition. And for this, I would like to invite Mr. Jayavardhan Kumar, senior scientist of this institute, to announce the winners. Jayavardhan, please.
धन्यवाद विवेक. मंचासीन मुख्य अतिथि प्रोफेसर ASK सिन्हा साहब, डायरेक्टर RGPIT अमेठी, संस्थान के ऊर्जावान निदेशक प्रोफेसर AK मिश्रा सर, मुख्य वैज्ञानिक डॉक्टर JK पांडे एवं संस्थान के प्रशासन नियंत्रक आलोक शर्मा जी, मुझे अत्यंत हर्ष एवं गौरव के साथ आपको यह सूचित करने में अति प्रसन्नता हो रही है कि आज राष्ट्रीय विज्ञान दिवस के शुभ अवसर पर CSIR-CIMFR में अंतर विद्यालय विज्ञान प्रश्नोत्तरी प्रतियोगिता का आयोजन किया गया था और हम अत्यंत आभारी हैं हमारे निदेशक महोदय का, जिन्होंने अपनी व्यस्त दिनचर्या से समय निकाल के इस समारोह का उद्घाटन किया और सभी छात्र छात्राओं को विज्ञान को अपने जीवन शैली में शामिल करने के लिए प्रेरित किया। तो इस प्रतियोगिता में कुल 8 विद्यालय, धनबाद के विभिन्न 8 विद्यालय सम्मिलित हुए थे, जिनका सारणी निम्न प्रकार से है। द्वारिका फाउंडेशन एकेडमी धनबाद, कस्तूरबा गांधी बालिका विद्यालय बलियापुर, धनबाद पब्लिक स्कूल धनबाद, कस्तूरबा गांधी विद्यालय भौरा, संस्कृति विद्या मंदिर डिगवाडिग, +2 जिला स्कूल धनबाद, उत्क्रमणित मध्य विद्यालय दलदली एवं उत्क्रमणित उच्च विद्यालय। तो कुल लगभग 80 छात्र छात्राएं इसमें सम्मिलित हुए थे और इन 80 छात्र छात्राओं में जिन लोगों ने इस प्रतियोगिता में पार्टिसिपेट किया, उसमें 3 विनर को हम लोगों ने सूचीबद्ध किया है। मैं आमंत्रित करना चाहूंगा अपने मुख्य अतिथि एवं निदेशक महोदय से कि वो हमारे विनर्स को प्राइज और सर्टिफिकेट दें। हम लोग स्टार्ट करेंगे 3rd प्राइज से। जो तृतीय पुरस्कार है वह जाता है द्वारिका मेमोरियल फाउंडेशन एकेडमी को। मैं नाम पुकारूंगा, वो नाम के अनुसार वो छात्र एवं छात्राएं मंच पर आए। अजीत यादव, पुष्पा कुमारी, धानु कुमार, कोमल कुमारी, द्वितीय पुरस्कार जाता है कस्तूरबा गांधी बालिका विद्यालय बलियापुर को। द्वितीय पुरस्कार कस्तूरबा गांधी बालिका विद्यालय बलियापुर, सबिता कुमारी, निशा कुमारी, पायल कुमारी, शिव कुमारी। टीम चलो जाओ। प्रथम पुरस्कार जाता है धनबाद पब्लिक स्कूल को। प्रतिभागियों के नाम है क्रमशः मुस्कान धर्मानी, आदित्य राज, शुभजीत चैटर्जी, आकांक्षा सुंडी। धन्यवाद सर। अब मैं अपने मित्र विवेक कुमार हिमांशु को आमंत्रित करता हूं कि वो आगे का कार्यक्रम के लिए मंच संचालन करें। धन्यवाद।
Thank you, Jayavardhan. Sir, this quiz competition was organized under the umbrella of CSIR Jigyasa program. And today's National Science Day lecture was uh, uh, also heard by our scientists from outreach centers through online portal, as well as this program was going live on YouTube, Facebook, and Twitter handle, our CSIR-CIMFR Twitter handle. Sir, we have tradition to honor our guest, and in this, I would like to request our director, sir, to honor our guest by presenting solemn memento. Thank you, sir. Now, I would like to request Controller of Administration, Mr. Alok Sharma, to propose a hearty vote of thanks.
Respected director sir, and today's chief guest of today's function, Professor A.K. Sinha Saab, Director Rajiv Gandhi Institute of Petroleum Technology, J.K. Pandey sir, and all student participants of, of the present in this hall, and their teachers as well. First of all, I would like to thank our chief guest, Shri A.K.S. Sinha sir, who has come all the way from RGIPT JAIS, which is far away, and sir traveled and took pain to be present with us. And sir delivered a very good lecture and very knowledgeable lecture. And what I could understand, the catch point of his lecture, that hydrogen shall be the future fuel. That's what I could understand. And carbon capture. So Sir, one important thing, or I also noted from your lecture that you have produced a technique from using IR. Means from IR waves, you can dissociate the hydrogen and oxygen. So it was very good technology of your institute. So, sir, I extend my heartily vote of thanks on behalf of institute to you. Secondly, I extend my vote of thanks to our director, sir, who is a perennial source of inspiration and guidance to us. And sir always provide cooperation and his guidance and gives all the encouragement to celebrate such programs like Science Day function. So, sir, I am very much thankful to you also, sir, for your continuous support to us. Now, I would like to thank Dr. J.K. Pandey Saab, coordinator HRD, who has took all the pain and responsibility to handle this function, Science Day function. So, sir, I think we have celebrated this function in befitting manner. So, sir, I thank to you also for celebrating this function. I extend my vote of thanks on behalf of the institute to all the students who participated in this event and their teachers as well, uh, and team of Jigyasa quiz competition, Kumkar sir and all his team who uh, uh, conducted this program in a proper manner of the science quiz. So thank to you also. I extend my vote of thanks to the evaluators of this Jigyasa program. Means evaluators means I think all judges who gave a quick decision for this program. So my thanks goes to them also. I am very much thankful to all staff members of our CIMFR family who attended this program physically and online and made this program a grand success. I extend my thanks to research scholar, project assistants, etc., who also took part all these events and give their kind support for this celebration. So my thanks goes to also them. I also thanks persons from press and media who always publicize our events of our institute in a at public at large in a positive manner. So thanks goes to them also. To celebrate any program, there are so many persons involved directly or indirectly. So I extend my thanks to all the person, one and all, who put their effort to make this program a grand success. Thank you. Thanks.
धन्यवाद। अब मैं आप सभी से अनुरोध करता हूं कि राष्ट्रगान के सम्मान में खड़े हो जाएं। सभी के लिए जलपान की व्यवस्था है, तो आप लोग